Greetings. Welcome to today's lesson. It's a two-parter on solving systems of linear equations by substitution. Now, in our previous set, we saw how to solve them by graphing. And graphing is very important because no matter what method we actually end up using in the end, we always have to keep in mind that when we're solving a system, whether it be linear equations or other, right? We're only looking at linear right now, but when we're solving a system, what we're really trying to figure out is where do the two equations intersect, okay? Whether we're looking only at linear right now, but it could be later on you'll be looking at one that's linear and one that isn't. And you want to know where do they meet. That's really the focus of everything we're doing. So being able to solve them graphically is kind of important because really where do they meet on a graph is what we're looking for. But what I love about this section that we're about to embark on, which is solving by substitution and eventually one called elimination, you're going to see that it allows us to sort of work outside the box. Even though what we're looking for is where do they meet on a graph, we won't need a graph to solve them. And that's what makes these really exciting. Okay, so, well, what is substitution? Let's just make sure we understand that. In fact, because we use this word all the time. In English, in everyday life, what the idea of substitution, in fact, I mean, heck, teaching, right? What's a substitute? A substitute is a replacement for me. This is a replacement of me not being in the classroom. I'm here with you virtually because I'm substituting this video for my actual presence. Okay, so the idea of substitution is just the replacing of one thing with another. Okay, and that one thing that you're replacing, hopefully what you're replacing it with is as good or the same as what you had originally. Okay, you substitute in a different teacher for the one that you should have. You substitute me personally for me virtually. You know, all of these sort of things. Now, when we do it mathematically, we do it all the time. In fact, we've done it quite a bit recently where we put in a value for x. We've substituted a value for x so we can then find the value for y. So we're choosing something to replace x with, to substitute in for x, to then figure out what we get for y. So what I'm looking at now is, so this is just replacing one value for another. And more specifically, when we start doing it with equations, we're going to substitute a whole expression for one variable, and when we do that, we will be left with an equation that only has one variable in it that we can solve for, and that's what makes this exciting. So let's take a look at what we're talking about. Okay, and again, they'll just give you a solve, right? Nothing spectacular, nothing tricky, nothing like elaborate, you know, they'll just say solve. Sometimes they'll say solve the system, sometimes they'll say find the solution of the given system. I mean, there's lots of ways to ask the same question, but really what we're trying to figure out is where do they intersect? And we've got two equations. We've got one, 2x plus y equals 4, and y equals 3x minus 1. So we've got two equations here. Now, in the past, what we would do is we would change this into slope-intercept form. It's not that hard, one step. We just move that 2x over here by subtracting it. And then we'd have two equations that we can do graphically. And we will, just so we can see. I want to bring this all back around to what does it look like when we solve an equation using substitution compared to how it looks if we were to have used graphing. Okay, but we're not going to solve this by graphing. This is where it gets exciting. We're going to solve this by substitution. Because what we have is, we have these two equations. One of them is in standard form, and one of them is in slope-intercept form. The one that's in slope-intercept form says that y equals 3x minus 1. Y equals 3x minus 1. Well, that means every time I see the letter y, I can substitute 3x minus 1 in its place. I have another equation with a y in it. So what I can do is I can rewrite it. And when I get to where it should be a y, I can substitute 3x minus 1. So instead of writing y, I got to write 3x minus 1 because that's what I'm doing. I'm substituting in the value. Now, if I just said, what would I, maybe I could have asked, what if y was 4? Then I could just put a 4 here and solve it. What if y was 8? I'd put a y in, I'd put an 8 here and solve it. But if you look now, what do I have? I only have one variable, x. So 2x plus 3x minus 1 equals 4. These two add up to 5x. And now I'm simply solving just like we did way back at the beginning of the semester. Way back at the beginning of all of these lessons. I have solved for x. Now I have not finished by any means, because remember, where do they meet on a graph? Well, where they meet on a graph is an x value and a y value, but I don't have that. All I have is an x value so far. Okay? So now what I can do is I can take this x value and I can plug it in, I can substitute it back in for x, and I can do it in either equation. In fact, I'm going to do both equations because just to prove to you, to show you that it has to give you the same answer, okay? Because remember, you're asking two equations. Where do you guys intersect? Where do you meet? If you ask two people where they meet and they give you a different answer, then they're not meeting there. So you're asking these two equations, where's your point of intersection? They better tell me the same thing, 1, comma, something, okay? So now I'm going to plug it into the first equation for the x. 2 times 1 is 2. Subtract the 2, and I get y equals 2. Now, I'm putting it in even though I'm not sure it's right yet. I think it's right, but I'm not sure. Okay, to be absolutely 100% certain, I'm going to plug this same 1 in for x in this equation. 3 times 1 is 3. 3 minus 1 is, hey, what do you know? It is 2. Now I am 100% certain that the point where these two lines intersect is the point 1, comma 2, and nowhere did I have to graph it. Even though when I worry about where they meet, I'm worrying about graphically where do they intersect. I don't have to worry if I do all this arithmetic, all this math, all this substituting. I have substituted this equation into this equation and solved for whichever variable was left. Now, would it have mattered if I had solved it, if I had found a way to replace x and done it the other way? No. Okay. I'm going to keep this answer here, and I'm going to keep those equations, and now I want to graph it because I want us to be able to see for certain that graphically we didn't get a different answer. So first I'm going to rewrite this one into slope-intercept form by subtracting 2x from both sides. And now I have my two equations, and now I can graph it. So starting here at 4, going down 2 and over 1. Here I start at -1. I go up 3 and over 1. And you can see very clearly they intersected at that point. I didn't quite draw it perfectly, but that's okay. But they clearly intersect at the point 1, comma 2. And if you plug those into each of these equations the way they're set up, you'll see it also works there as well. Okay. All right. So let's look at one more system. Okay. And now we're not even gonna worry about the graph. We're simply gonna solve one more system. So, okay, let's go 2x plus 3y equals 6, and Let's make this a little more challenging for myself. Let's go x minus y equals, so let's see, let's say 3. Okay. Neither of these equations has either of the variables isolated. So now we got a problem because there's nothing I can't replace. I mean, if I had a 3, I could replace, I don't know. So what you need to do here is, isolate the variable. Which variable? Doesn't matter. You need to isolate one of them. So you look at equations, you can decide which one you like, which one looks easiest. We'll see this again in the next follow-up. I'm going to go with the second equation. I really like getting things into slope-intercept form. So I'm going to do that, even though it's not the easiest way. We'll talk about the easiest way next time. So I have x minus y equals 3. I subtract x from both sides. And I divide everything by -1. And now I can replace the y with x minus 3 into this equation. So 2x plus 3 times, and you notice I put the parentheses last time, but now it really matters because I have 3y, I have 3 of this x minus 3 thing, and that equals 6. And again, notice now I only have one variable. I'm solving my one variable, following the inverse order, still dealing with the exponent, the parentheses first. 3 times x is 3x. 3 times -3 would be -9. Combining my like terms here is 5x minus 9 equals 6. Add 9 to both sides. 5x equaling 15. And dividing by 5, x equaling 3. Now I'm getting nice, neat whole numbers, and I'll be honest, that was by design. I gave myself easy ones. There is nothing that says these couldn't come out as horrible, awful fractions like 2/3, 3/7, 5/8, who knows? Okay, but I tried to make it easier on myself, just in the long scheme of things. And again, I can put it into either one. If I'm ever going to substitute it, never go into one that you've already modified, because if you've made a mistake, you won't catch it. So always go back to an original equation. Okay, so I'll go back to the second equation there. 3 minus y equals 3. Oh, hey, that looks pretty easy to me. Subtract the 3. Negative y equals 0. Y equals 0. And I could check that total. I could check that in total. I could say, well, does 2 times 3, which is 6, plus 3 times 0, which is 0, does 6 equal 6? Yeah, it does. So that is definitely where those two lines intersect. And again, no need to graph. Nothing here is graphed. It's all done what we call algebraically, using a method called substitution. And you can do this with much more complicated equations than we're working with, right? Linear equations are probably the easiest we're going to see. When you get into high school and beyond, you might see equations that are not linear. They're called quadratic. You might even see things beyond that, where you might have to figure out where does a line hit a curve. And one of those, so you have a linear equation and you have a nonlinear equation, and you use one to solve the other. Okay? It reminds me of an old riddle. It's always one of my favorites. If you know one person always tells the truth and one person always lies, and you have to get behind, you need to go to the correct door. And they tell you one of these doors leads to great riches and the other leads to certain death. One of these guys they'll both tell you one answer. You may ask one question, and one always tells the truth and one always lies. What do you ask? Well, what do you ask? You ask one guy, what will the other guy tell me is the door to riches? Because if they'll both give you, because you get the same answer that way. The liar will lie about what the guy who always tells the truth would tell you, and therefore you've been told a lie. The truth teller will tell you that he's going to lie, and therefore he's going to tell you this, which is a lie. So either way, you're going to be told a lie. So whichever door they tell you to take, you take the other one. I'm asking two equations, where do you meet? They better tell me the same thing. Okay, so I better get the same answer regardless of which one I plug into which one, regardless of which variable I solve for. I could have solved this one for x, and you'll see that in the next video. And when I do that, I would have found y first and x second. It wouldn't have made any difference. I would have still found the same thing, that y is 0 and x is 3. Okay, I hope that helps, and otherwise I will see you in class.